Hi, we are now going to be learning about complex numbers in polar form. So let's quickly recap what we did in the last lesson. For complex numbers, they are basically written as x plus jy, where x is the real part and jy here, that is the imaginary part. This is what we call the rectangular form. Okay, the rectangular form of a complex number. Now we can convert this complex number from rectangular form to another form known as the polar form. Okay, and the polar form basically is represented by two parameters, which are r and theta. Okay, let's look at a simple complex number here. Let's say I give you this number 2 plus j3. Okay, how would you draw this in the complex plane? So you have your real axis and your imaginary axis here. So 2 is the real part, so 2, and j3, so 3 will be here. So the complex number would be drawn, okay, like this. Now when I wish to represent the same complex number in the polar form, we need to find r and theta. R is actually this length here, the length of this vector that I've drawn. As you can see, this is actually, okay, as you can see here, this is actually a right angle triangle, which means this r, okay, this r here is actually the hypotenuse. If you remember right angle triangles, a very popular formula associated with right angle triangles is the Pythagoras theorem. Okay, I'm not going to go into the maths about it, but very simply put, Pythagoras theorem says, okay, given any right angle triangle, okay, let me draw this a bit properly here. Yep, so given a right angle triangle, if I label these sides as A, B and C, the Pythagoras theorem says that the square of the hypotenuse is equals to the sum of the squares of the other two sides. So that means r square is equals to, okay, x square plus y square, because x here, in this case, this is your x and this here is your y, and that implies that r is equals to the square root of x square plus y square. So that is the way you find r. So how about theta? Theta is actually this angle over here, this angle here. So that angle here is theta. And as you can see, this, since this is a right angle triangle and we know x and y, for this angle theta, okay, for this angle theta, we can say that the x is the adjacent. Okay, so these are all referenced with our right angle. So if I put this as theta over here, all right, for theta, A is the adjacent. So for here, this theta, x is the adjacent, and y is the opposite. In this case, B is the opposite. And the trigonometric identity that we can, or trigonometric formula that we can use, okay, that relates opposite and adjacent, is basically the tangent. So the tangent of an angle is equals to the opposite over adjacent, which means that tan theta in this case is equals to y over x. Okay, and from there you can derive theta to be equals to the inverse tangent of y over x. So that is basically how you can convert a complex number from the rectangular form to the polar form. Now, let's look at an example, okay, and work it out. Let's say you're given this expression. Okay, so this is the understanding part. Now we're going to look at some examples. Okay, so 3 plus j2. Okay, so 3 plus j2, if we relate it back to our generic expression x plus jy, so x is 3 and y is 2. From there you can find your r. We saw that r is the square root of x square plus y square, which is square root of 3 square plus 2 square, which is 9 plus 4, 13. Okay, and for the angle, we can say that tangent theta is equals to y over x. Okay, and tangent theta can be written as 2 over 3. So theta is equals to inverse tangent of 2 over 3. If you key that in your calculator, so in your calculator you must remember that you will see the trig functions sine, cosine and tangent, and usually for those same buttons you have an inverse right on top of it. Okay, so you must usually enter shift tangent to get the inverse tangent function. Okay, so if you do that, you will get the answer as 33.7 degrees. That means 3 plus j2 in rectangular form can then be expressed as square root 13 angle 33.7 degrees in polar form. So that is the conversion over here. Now let's try another example. Okay, so if I give you another complex number 1 plus j7. Now 1 plus j7, if you relate it back to our generic expression x plus jy, you will see that x is 1 and y is 7. So r is given as square root of 1 square plus 7 square, x square plus y square. Square root of 1 plus 49 will be 50, which is, yeah, you can just leave it as that for now. And tangent theta is equals to y over x, which is 7 over 1. So theta is equals to inverse tangent of 7, which is 81.9 degrees. So that means 1 plus j7 can now be represented as root 50 r angle 81.9 degrees. So that is the representation here of or the way in which you convert the complex number from rectangular form to polar form. Now, since we can convert from rectangular to polar, we must also be able to convert from polar to rectangular. Okay, so now what we're going to do is we're going to learn how to convert from polar to rectangular. Okay, now what we have seen is in the polar form, the complex number is represented as r angle theta, and in the rectangular form you have it represented as x plus jy. Okay, so I must be able to derive x and y given r and theta, and the formula is given as this, where x is r cosine theta and y is r sine theta. Okay, now let's look back at what we just did. Okay, so I'm going to take this polar form here, square root 13 and 33.7 degrees, and let's see how we can convert it back to its rectangular form. Okay, so I have uh, the rectangular form given as square root 13 angle 33.7 degrees, and to convert it to uh, rectangular form, I follow this formula here. So the x is r, which is square root 13 cosine 33.7 degrees plus r sine theta 33.7 degrees, and that will give me 3.6 here. Cosine of 33.7 will be 0.83 plus so here I must remember to put a j, okay, because this is the imaginary part. Okay, so plus j 3.6 and 0.55, and if you key those numbers in your calculator, you'll get the answer as 3 plus j2, which is the same as the rectangular form of the complex number that we started with earlier. Okay, so let's do it for the second number just for practice. Okay, so the second number is given as square root of 50 angle 81.9 degrees, and now we're going to convert that number from its polar form to its rectangular form. So the formula says it will be r cosine theta plus j r sine theta. Okay, so put in the numbers. Okay, so all this you must use your calculator. 0.14 plus j 7.07 0.99. Okay, and that will give us 1 plus j7. Okay, and as you can see, this is the same as what we had earlier. Okay, so now you have learned how to convert a complex number from rectangular to polar and polar back to rectangular. So right now what I'm going to do is focus on uh, what are the benefits, okay, of converting them to polar form. The main benefits are in the areas of multiplication and division. For two complex numbers, okay, so if I have a plus jb and I have another complex number c plus jd, and I ask you to perform the multiplication. All right, so right now we're going to focus on the multiplication part here. Okay, and if I ask you to do the multiplication in rectangular form, what you would do is you would have to write it out in by placing them side by side, and then you would do your expansion. Okay, so we have actually covered this in the previous video of how multiplication can be done in the rectangular form. So right now what we're going to do is we're going to show you how you can actually do it much more easily when the complex numbers are in the polar form. So I'm going to convert both of them to their polar form. So a plus jb will be r1 angle theta 1, and this would be r2 angle theta 2. So when I want to do this multiplication, okay, of these two complex numbers, the way to do it, okay, when they are both in their polar form, okay, so write them out in their polar form. Okay, the way to do it would be very simple. You just need to multiply the two r values, so it will be r1 multiplied by r2 followed by adding up the two angles, theta 1 add with theta 2. Okay, so that is all you need to do. Now let's look at this example where we're going to multiply the two complex numbers we saw earlier. So if I have 3 plus j2 and I have 1 plus j7, to multiply them together in the polar form, I make sure that I first do the conversion, which we have already done. So this complex number is square root 13 angle 33.7 degrees, and this number here is square root 50 angle 81.9 degrees. And the next step, like what I've shown you here, is you multiply the R values together and then you add the angles together. So 33.7 degrees plus 81.9 degrees. Okay, so the rest you need to put in your calculator. So what you will get here, square root 13 times square root 50, you get 25.5. Okay, and the angle you will get is 115.6 degrees. Okay, now if I were to convert this back into its rectangular form, okay, if I want to convert this back to my rectangular form, I do take the same approach as just now, which would be R cosine theta plus J R sine theta. Okay, so all of this is basic calculations you can use perform with your calculator, and the answer you would get would be minus 11 plus j23. So you can confirm this answer by performing the expansion method that I showed you in the previous lesson. Okay, now let's move on to some other interesting examples as well, okay, for us to try it out. Let's look at this question here. 1 minus 5i multiplied by minus 9 plus 2i. Okay, so for us to do this, we must first convert each of them to their equivalent polar form. Alright, so let's do it one by one. So the first complex number here, 1 minus 5i. To convert it, I need to find r and theta. So it would be 1 square plus minus 5 square, and the angle would be inverse tangent of negative 5 over 1. So that would be square root of 26, okay, angle of negative 78.7 degrees. Okay, so negative 78.7 degrees. How do you relate to this? Okay, so this is where you must have some visualization of how this particular complex number is actually going to look like. Okay, so as you can see, this number here is 1 minus 5i. So if I were to draw the complex plane here, this complex number would be 1 here in the real domain, real axis. Okay, so this is the real axis, this is the imaginary axis. Under the imaginary part, it would be here, minus 5. Okay, so I would have drawn it this way, which means this angle negative 78.7 is actually representing from here going in this direction. Okay, so the actual theta is actually in this direction. Correct, so theta in this case is equals to 360 degrees minus 78.7 degrees. Okay, so you must know where the complex number is going to lie, in which quadrant, and from there you must know where how to find the correct theta that you're going to use for your calculation. So in this case, the theta here is 281.3 degrees. Alright, so here I need to rewrite the angle as angle 281.3 degrees here. Okay, so this again is based on analyzing where or in which quadrant each complex number is going to be in. Okay, so let's look at the second complex number, okay, and then we will see another example of this. So the second complex number is minus 9 plus 2i. Okay, and I'm going to do the same thing. I'm going to convert it to its polar form. So this will be minus 9 square plus 2 square, and the angle is inverse tangent of 2 over minus 9, which will be equals to so over here will be square root 85, and if I key that in my calculator, 2 over minus 9, I do an inverse tangent, I'll get negative 12.5 degrees. Okay, now negative 12.5 degrees, where is that? So we must again do the same process of drawing out your complex plane and looking at this number minus 9 plus 2i. So it will be here minus 9 and plus 2 is here. So this is the point. So the complex number lies in this quadrant 2. So this negative theta in this case is referring to this angle over here. Okay, so this is your negative 12.5 degrees. So the actual theta that we want is actually this theta here. And this theta would be 180 degrees minus 12.5 degrees, which is 167.5 degrees here. So I then need to rewrite the angle here as square root. So the r remains the same. The angle will now be rewritten as 167.5 degrees. Okay, so as you can see, the tricky part is when you get the angle, when the angle is negative, you need to analyze which quadrant the complex number is going to lie in, and from there you need to deduce the actual angle. Okay, so now that we have actually converted both of them to their complex numbers, we can proceed to perform the multiplication in the polar form. So square root 26 angle 281.3 degrees and square root 85 angle 167.5 degrees, and it will be the two r's multiplied by each other, and the two angles at which is with each other, 281.3 degrees plus 67.5 degrees. Okay, so I will get 47 angle with 448.8 degrees. Okay, when you get an answer that is bigger than 360, you know that it's actually gone one full circle already, correct? So as long as the answer is more than 360, that means it has already gone one full circle and is now carrying on again. So in that case, you can say that the final angle would be 448.8 minus 360 degrees, which will be 88.8 degrees. So the final answer here is 47 angle of 88.8 degrees. Okay, you can of course convert this back to its polar in rectangular form, okay, by using the approach that we have seen so far, which is to say it is r cosine theta plus j r sine theta. Okay, and that will give you an answer of 1 plus j47. Okay, so you can of course confirm this answer by doing the actual multiplication in the rectangular approach. That means you do the expansion. Okay, so what we have seen is we have seen the application of the polar form approach in multiplication. Now we're going to do it in division. Okay, so for division, what we have is given two complex numbers, r1 angle theta 1 divided by r2 angle theta 2. What you will get is r1 over r2. So only the r values you divide and the angles you subtract. Theta 1 minus theta 2. Okay, so let's try this, okay, with a real example. So 3 minus I divided by 2 plus 7I equals to, so we're going to convert both of them to their actual polar forms. So it will be square root of 3 square plus minus 1 square angle inverse tangent of minus 1 over 3 divided by square root 2 square plus 7 square. Angle is inverse tangent of 7 over 2. Now what you have is the numerator, you get square root 10 angle of a negative 18.4 degrees divided by square root 53 angle of 74.05 degrees. So the numerator part, as you can see, it is a negative angle, so we need to do the analysis. So let's draw the complex plane. So this is the real part, this is real axis, imaginary axis. So 3 is here, minus I is minus 1 here, minus 1I. So the complex number lies in this quadrant, which means the theta was actually this, correct? Now the negative 18.4 is this, and that implies that the real theta that we must use is this angle here, which is 360 degrees minus 18.4 degrees, which is equals to 341.6 degrees here. Okay, so I'm going to write that new expression here. So square root 10 angle of 341.6 degrees divided by square root 53 angle 74.05 degrees. Okay, and now we can apply the rule that we just saw. Two complex numbers divided by each other, and they are both in their polar form, which means the r values you divide them, okay, and the angles you subtract them. 74.05 here, and you get 0.434 angle 267.6 degrees here. Okay, if you were to convert them to the rectangular form, okay, you can do that, and what you will get is 0.434 cosine 267.6 degrees plus j 0.434 sine 267.6 degrees, and that would give you minus 0.018 minus j 0.434 4. We can confirm that this is the correct answer by performing the division based on the rectangular form approach, like what we learned in the previous video, where you need to multiply the numerator and denominator by the complex conjugate of the denominator. Okay, so if you need to revise on that method, please look back at that earlier video. Now let's look at just one more example, okay, on a division here. So we are now given this question, 3 over 9 minus I. Now how do we proceed with this? Okay, for the denominator, okay, it's quite straightforward, okay, where we just proceed to keep it as it is, 9 minus I. But the numerator, as you can see, doesn't seem to have any imaginary part, correct? It only has a real part. So the imaginary part is effectively 0. Okay, it's effectively 0. So you can just write it as 3 plus I0. Okay, 3 plus I0. So that is an easy way to proceed with this question. Okay, so you may look a bit complicated because suddenly only the numerator, only the denominator is a complex number, but the numerator is just a real number only. Okay, so you can actually write it as a complex number by just writing a plus I0. You can do, or you can perform the same technique if the numerator was just only a imaginary part. Then I put a 0 as a real part to the complex number. So with that, the rest becomes the same as what we have been doing all the while. Okay, so let's proceed. So the numerator will be 3 square plus 0 square, square root, inverse tangent, 0 over 3. For the denominator part, you have 9 square plus minus 1 square. Angle is inverse tangent of negative 1 over 9. Okay, and then we have this numerator, which will be, so 3 square, square root, you get back 3, and this 0 divided by 3 is 0. Inverse tangent of 0 would also be 0. Okay, and in the denominator, what you have is square root 82, angle of a negative 6.34 degrees. Okay, as we have seen just now, when the angle is negative, in this case, we need to draw the complex plane and see where it lies. So this is the real part and this is the imaginary part. So 9 minus I, so 9 will be here, minus I is minus 1. So the complex number is actually represented by this vector here, which means that the theta, negative 6.34 degrees, is this angle here. So the actual angle that we need to look at is this angle, which will be 360 degrees minus 6.34 degrees, and that will give us 353.66 degrees. So we can now proceed to write that here. So I got 3 angle 0 degrees followed by square root 82 angle 353.66 degrees. Okay, and then let's proceed on. So the next step would be, we see that right now what we have is we have a complex number divided by another complex number, both of them in the polar form, which means I can now apply the formula that we have seen, where the R1 divided by R2, and the angle would be subtraction. So it will be 0 degrees minus 353.66 degrees. Okay, so what you'll get is 3 over square root 2, you get 0.331. Okay, and you'll get minus 353.666 degrees. Okay, so since this is a negative angle, we again need to do the same thing. Draw the complex plane. This is the real and this is the imaginary. Okay, so negative 353.66 means is going in the opposite direction, so the angle actually went in this direction. And 353.66 means is going up to 4 quadrants but in the opposite direction. So we know that the eventual angle would be in the first quadrant here. Okay, so this angle here will be 360 minus 353.66 degrees, which will be 6.34 degrees. Okay, so what you have here finally is 0.331 angle 6.34 degrees. Okay, and of course you can convert this to its rectangular form as well. If you do that, okay, what you will get is 0.331 cosine 6.34 degrees plus j 0.331 sine 6.34 degrees, and that would give you 0.328 plus j 0.0366. Okay, and as you can see, this corresponds to a vector, okay, a complex number in a vector form in the first quadrant here, because this is positive, so 0.328 somewhere here, and this is also positive. Okay, so you'll be here and here, so you draw the vector somewhere in this direction. All right, so with that we can conclude this lesson on complex numbers in the polar form. All right, so what we have seen is we have seen the conversion from rectangular to polar and polar to rectangular. Followed by that, we have seen the multiplication, and we have concluded with the division. Okay, so in this lesson, we have learned quite a lot of important concepts on how to deal with complex numbers in their polar form. All right, so thank you very much for watching, and see you soon in the next video. Thank you. Bye.